Yes, in the last video, we looked at what a discrete random variable is and what a discrete distribution function is. And as I have already announced, we want to take a look at what a continuous random variable is, what it has to do with the distribution function, and why integrals come into play now. And with that, let's get started right away. The idea is that we define the concept of a continuous random variable through the distribution function. A random variable is called continuous if its corresponding distribution function can always be defined. Imagine we have our random variable. We can always define the function that represents the probability that x is less than a given x. We can do this just as we do for discrete random variables when this function is continuous. And we want to illustrate this with a short example. The example is the height, and we also want to take a closer look at the difference between continuous and non-continuous distribution functions. Height, in general, looks approximately like this. So, what do we see here now? We see the distribution function of height here. This means, just to clarify once more, if we take a value here, for example 170, then this value indicates the probability that a person is less than or equal to 170 km in height. And this probability is smaller than the value at 180. Well, why? The probability of being less than 180 centimeters is more than the probability of being less than 170 centimeters. There is a larger range allowed. And continuous means, in this case, perhaps you learned this in school, it means I have a kind of curve that I can draw without lifting my pencil, or, as it is also said, without having jump points. And that is simply because, why do we not have jump points here? If we look at how likely it is to be a little bit smaller, that is, smaller than 170 plus, a very small number, so smaller than, for example, 170,001, then this is roughly equivalent to the probability of being less than or equal to 170,000. This means that if I move a little to the right on the function in the graph, I also move a little up, and not like we have seen it before. In the function, let's maybe go back for a moment. In this function, we have here, where we see that if we take a very small step from 4, for example, here we have a double dice throw. If we move to the right, we then make a huge jump. And that would be, so to speak, the opposite of a continuous distribution function, if we have jump points at finitely many places. Well, this is a continuous random variable, and you can see that we must also have infinitely many values occurring here, because otherwise we wouldn't be able to draw such a smooth, continuous curve. Otherwise, we would have jump points somewhere. This means that one side effect of this is that it involves infinitely many values that can be assumed, and that makes sense, because any possible size is conceivable, as precise as desired to any decimal place. Well, this is a continuous random variable. Now let's take a look at how we can examine such a probability distribution. We can assign them. However, because we have infinitely many values, we cannot specify them anymore. We also cannot list the pi's and the she's. This means we need a different concept. And another observation we make is the following. Namely, if you ask yourself, what is the probability of taking on exactly one value? So, in our example with height, what is the probability of being exactly 1.80 meters tall? Or, in other words, 180,000, and so on centimeters. Then the answer is that the probability is 0, because the possibility, so to speak, is that you can always change a decimal place, so to speak, so that this value does not hold. So to speak, this height is not reached. This means that hitting exactly one point, exactly one height, has a probability of 0. And that is a bit counterintuitive at first, because what we actually have is, well, I will mark this here. First, that the probability of reaching exactly one value is indeed 0. This is a bit counterintuitive because the probability, when I sum them all up, for each possibility equals 1. And we need to somehow resolve this a bit. And now you might also see why we cannot simply provide an infinite number of values for which the probabilities reach a value, as we did with the discrete distribution, because all these values are 0. And so we need an alternative concept, and that is the probability density. We cannot specify how high the probability is of hitting exactly the point X. It is actually 0. But we can say that it is more likely to hit there than over there. That already makes sense. The probability that someone is around 180 cm tall is greater than that of being around 220 m tall. And we want to be able to represent that somehow. And that is the probability density. And it goes as follows. We are now using differential and integral calculus here. And we have the following definition. So we have our continuous random variable. And we also want, which is a condition we set, that the distribution function should not only be continuous, but also differentiable, or at least piecewise differentiable. This means that I can form the derivative at a certain point. Why do I want the derivative? Because the derivative, which we call f, is what we refer to as the density function. And conversely, this is a density function. So this is a value at a point to which we can assign a value. Conversely, if we can specify a density function, then we can say, according to the fundamental theorem of calculus, that the antiderivative representing the distribution function is given by the integral from negative infinity to x. So we essentially obtain the distribution function from the density function through the integral. Let's take a quick look at this again in the example. Here we can see it quite well. On the left side, you can see what we looked at earlier, which is the distribution function of height. And now we will derive it once, and then you will see that is the density function. The interesting thing you are seeing now is that what I just mentioned, namely, that it is more likely to fall within the range of 170 centimeters than within the range of, for example, 210 centimeters. So when we compare the value here with the value, we see it exactly in the density function. Namely, the density is much higher at this point, 170 centimeters. And why? Well, because at this point, the function rises particularly steeply. This means we don't have jump points, which represent our probabilities in the discrete distribution function, but we do have slopes that essentially describe that the whole thing becomes more likely here. And that means the density function is the method of choice to describe a distribution more accurately. And what I also want to emphasize here is that we have now seen one relationship regarding the slope. On the right, the slope from the left is represented, but now we see the reverse representation here, namely on the right side. When we take the area, for example, up to 180, we get the value at this point, namely the value at 180. So the area of the density describes the distribution function. And that is exactly this main theorem of differential and integral calculus that needs to be taken into account. Well, if we have understood that, then let's take a look at another important statement. This is a bit of a refinement of the observation we made, namely that when we want to look at probabilities that x lies within an interval, for example in a closed interval, it doesn't matter whether the interval is closed, half open, or half closed. It's all the same because the probability of being exactly at the value a or b is anyway 0. This means that whether I write less than or equal to or just less is completely irrelevant. And the nice thing is now I can also determine this probability through the density function. On one hand, it is naturally the distribution function of b minus, the distribution function of a. So I look at how high the probability is that it is less than or equal to b and subtract the probability of it being less than or equal to a, then I get exactly the interval. This works just like in the discrete case. And if we now apply the fundamental theorem of differential and integral calculus again, then it is nothing other than the integral from a to b of the density function. In other words, here it is again as an image. If I look at the interval from 160 to 180, I can either take the value here minus the value here, or I can take this area here. That is nothing other than what this statement says. And so that is a continuous random variable. As you can see, it all gets a bit more complicated because we need integrals. And that's why we want to look at two examples. In the next video, where we will examine two distribution functions and determine their density, or rather take a closer look at the feedback between density and distribution function. Until then,